The dimensioning and tolerancing is a critical part of any design. It requires knowledge about the manufacturing technology capabilities, the economy of production, and most of all, the function of the design product, which is easier said than done. The automotive differential was found to be interfering with the gearbox housing. This was a single event, but it raised questions how likely it is to repeat. Through the inspection of the components, it was found that the critical dimensions in the used parts conform to the specification, and moreover, that the process capability was also within acceptable limits. Only after a thorough analysis of the non-critical dimensions it was found that the combination of the individual dimensions caused the problem. There was not any single one that was wrong, and there was not even a dominant contributor to the problem. It was a coincidence arising from a specific combination of dimensions and working conditions. Since this was a mass-produced assembly, the question still remained. Was it a single event that will not repeat in the future, or should there be changes to the differential dimensioning and tolerancing? Let's have a look at the tolerance analysis in general. We all know the one-dimensional tolerance analysis. But when it comes to the real-life cases of mass-produced goods, things become complicated. For the 2- and 3-dimensional cases, the task cannot be solved as easily. In the one-dimensional case, we have the possibility to review all the contributing tolerances with respect to some functional dimension. This functional dimension has its known minimum and maximum, and the contributing tolerances shall be calculated so that it is attained. We can make a simple equation and calculate it for the minimal and maximal case. Piece of cake. And now let's see a simple 3-dimensional case. Suppose we need to fit upper part of housing on 4 pins in the lower part. We can calculate the resulting clearance in the connection points, but as you can see, the equation is much more complicated. And the complexity is not yet the problem. When you look into the equation, you will see that it no longer follows the pattern of minima and maxima. Sometimes we can guess which one to use, but there is not a general rule. If we want it to be on the safe side, we need to calculate all combinations. With just 20 tolerances, there is over 1 million of min-max combinations, and for some specific cases, the extremes in the resulting clearance do not even have to be a combination of the extremes. It makes this type of calculation quite impractical, and when the number of tolerances rises to mere 60 or 70, it is actually impossible, even with the fastest computers running for months. The presented calculation may be okay from the functional point of view, but it is lacking the economic component of the production. The exact cost is, of course, very specific, but there is a general rule. The smaller the tolerance is, the more expensive is the production. The design task is therefore to make the tolerances as wide as possible and still meet the functional criteria. Let's see the one-dimensional case again, but now with the statistical approach. The statistical tolerance analysis allows justified extension of tolerance limits in comparison to the min-max calculation. Suppose the process capability index is more than 1, and therefore the probability of each part being out of tolerance is 0.27%. So the probability that all 5 parts will simultaneously be out of specification is approximately 1 in 7 trillions. That is quite unlikely and overly conservative. Except for some really important cases, we can accept the resulting functional tolerance to be on the general capability level, yielding approximately the 0.27% risk. So, how much bigger can the individual tolerances be? The simplest textbook-like solution would be: assume normal distribution and independency in the tolerances, and so the standard deviation of the resulting dimension is Pythagorean sum of the individual standard deviations. When all these are the same, the individual tolerances can be extended by the square root of the number of tolerances used. In our case, they all can be extended by about 2.2, making the production notably easier and cheaper. Not all cases are as favorable, and not always we can use the textbook assumptions. First, the distribution may not always be normal, and second, the individual tolerances may be correlated. In these one-dimensional cases, we may be able to guess this based on the past experience or from the fact that the 2 spacers are likely from one batch. But mostly we will see the complete picture only after the production is running. Both the distribution and the correlations will influence the result. In these cases, we can no longer use the simple Pythagorean sum. The most practical approach is to use the Monte Carlo method. The principle of the Monte Carlo simulation is to randomly generate a number of components and use them in the calculation. The randomness, of course, has its specific properties corresponding to the properties of the tolerances. In this way, we can generate various distributions and also their mutual correlations if needed. For each of the simulated cases, we can calculate the resulting specification parameter and evaluate all of them as a statistical sample. This sample will then show if the risk of being out of the desired specification is low enough. The same method can and should be used also for the multidimensional cases. The primary benefit: we don't need to calculate all combinations as long as we have a representative sample. This will suddenly turn the impossible task to a feasible one. In these cases, we very often deal with a number of dimensions in each of the part, and these are very likely to be mutually dependent. For example, when the bottom part is positioned for machining, all pinholes will be shifted by the mounting deviation in the same direction. They will not be independent. Sometimes these dependencies cannot be described by a simple correlation matrix, because the correlation only accounts for linear dependencies. And this was exactly what happened during the manufacture of the differential components. Sometimes the reality is a little too much even for advanced tolerancing software. In these cases, The correlation matrix is not an adequate description of the case, and we need to use the multivariate probability distribution instead. When the risk of collision was calculated using the actual dependencies, it proved to be more than the acceptable level, and the problem was likely to reoccur. Since the data from this analysis was already available, it was used to make changes to the tolerancing, as it already reflects the dependencies between the contributing tolerances and the resulting specification. This method is very efficient in estimating of what may happen during the production and assembly. It is not physically possible to test all the different scenarios, not to mention different variations in the design. Even the use of simpler methods can bring better understanding of the future risks. Sometimes a simple manual calculation is sufficient, but sometimes we need an advanced software. The principle is always the same. We try to make a model of reality, and we use this model to find what are the properties of reality beyond what we can actually observe. When dealing with random quantities, which is absolutely most of the time, the use of statistical perspective in the calculation will always give better estimates. In any case, the choice of the method must be driven by the knowledge of its advantages and limitations. And keep in mind that every model, no matter how advanced, has its limitations.